Hi, welcome to another video. Today we are going to talk about read committed isolation. So let's get into it. Before we talk about read committed isolation, first we need to understand what is isolation. If you remember from an earlier video, the I in the ACID is the isolation. So what is isolation? This is a property of a database which guarantees concurrent transactions, they don't interfere with each other. And what is the goal? The goal is to maintain data integrity. And of course, it does not come for free. We have to balance the consistency with performance. So let's talk about it briefly. In an ideal world, when there are two transactions happening, so for example, there are two rows, row A and row B. They are touched by transaction 1 and also transaction 2 touch them. And the isolation tries to guarantee that transaction 1 and transaction 2, as they work on the same set of rows, they don't interfere with each other. Let's say we transfer money from account A to account B and we transfer $100, let's say. So from A it will be -100 and at B it will be +100 after the transaction is done. So we are trying to say by isolation is that transaction 2 does not interfere with transaction 1. By that I mean transaction 2 does not see the data or write the data to A or B while transaction 1 is still ongoing, so that it does not read or write any dirty value. Now let's get into what is read committed isolation. So what is read committed isolation? What is the definition of it? The definition is that a transaction can only read data that has been committed by other transactions. Going back to the previous examples, let's say there are A and B, there are two rows, and transaction 1 is currently acting on them. So if transaction 2 comes and it tries to see row A and B, it does not see the values that transaction 1 has already updated them to, because transaction 1 is still ongoing. The transaction 2 only sees the values that have been committed by some transaction. So it can be a previous transaction which updated A and B last, and that transaction has committed already. So transaction 2 sees that value. It does not see an intermediate value that is currently in transaction 1. So why do we do it? It stops the dirty read anomaly, and you will never read uncommitted data. What is the problem? So let's say transaction A reads data written by transaction B, and B then rolls back. Then A's read was incorrect or invalid. So it is pretty clear to understand. So let's say again row A, row B, and there is transaction 1, and A and B initially their values were 50 and 50, and transaction 1 was trying to transfer 10 from A to B. So at the end of the transaction it would be 40 and 60. But let's say and then let's say another operation comes, which is transaction 2, which let's say it tries to deduct $50 from both A and B, but it can't deduct $50 from any of the accounts if the account has less than $50. What will happen in this case? If transaction 1 is currently acting on it and transaction 1 deducted $10 from A, but before adding the $10 to B, the database ran into some error, so we need to roll back. If transaction 2 were able to actually read these dirty values, then there would be a problem. Let's say the transaction was rolled back before it was updated to 60. Transaction 2 would read 40 and it could not deduct $50. But because transaction 1 was rolled back, actually transaction 2, if it would read the committed value, it would actually read A and B both $50, and it could deduct $50 for both of them. A's read was incorrect or invalid. In our case, transaction 2's read was actually invalid because transaction 1 was already acting on it. So how do we fix this problem? One fix is the serializability, where transaction 1 and transaction 2, they completely are executed one after the other, but that can reduce the performance of the database because the read and write requests, everything that happens inside a transaction, they are queued up one after the other. So another alternative is let that transactions happen, but transaction 2 can only see the committed data from A and B. So for example, when transaction 1 is ongoing, transaction 2 can only see the committed data of A and B, which is $50. Let's understand how do we actually implement that. So each of the rows, they have to maintain two sets of values. One A has to maintain 50 and maybe 40 while the transaction is 1 is ongoing, and B has to maintain 50 and 60 when transaction 1 is ongoing. The database understands when transaction 1 is ongoing, the 40 and 60, they should not be returned, only the 50 values should be returned to another transaction. But when transaction 1 is committed, the updated values would be 40 and 60, and in that case we don't need to maintain the old values, and only the new values would replace the old values, which are 40 and 60. If another transaction 3, it tries to read the value, they will read values 40 and 60. So of course you can understand the read committed isolation is not perfect, and we are trying to guarantee some consistency, but not fully, not as much consistency as serializability offers, because we also want to keep the database fairly performant. So what are the errors that can still happen with read committed isolation? Again, going back to the previous example, let's say I have two transactions now. There is transaction 1 again, which transfers $10 from A to B. So let's say they have $50 each, and A to B, they can have 40 and 60 after $10 transfer. And now another transaction 2 comes, and let's say transaction 2 only reads the values of both A and B at the same time. So when transaction 2 comes, first it reads the value of A, and when it gets the value of A, then it says $50. But let's say due to network delay or some other issue, when it tries to read the value of B, the transaction 1 has already committed, and in that case transaction 2 reads the value $60 of account B. So what is the total amount of money transaction 2 gets? It is 50 plus 60 equal to 110. So we are reading $10 extra, and that is not possible. That's why it is called non-repeatable read anomaly. If there is another transaction 3, which tries to read the values of A and B again, it will read both 40 and 60, and the sum would be 100 again. But because transaction 2 only reads the committed values of both A and B, this kind of anomaly is allowed under read committed isolation. There is another type of anomaly, which is phantom read. So let's say there are transaction 1 and transaction 2. Transaction 1 inserts a row between two rows in a database, and then transaction 2 comes and reads all the data. And transaction 2, as you can see, although it may start before transaction 1 starts, it can still read one extra row when transaction 1 is finished with it. So this problem is called phantom read anomaly, which is allowed. So we briefly touched upon how implement the read committed isolation by multi-version concurrency control, because each row has to maintain 2 sets of versions at most to maintain read committed isolations. And this multi-version concurrency control, or MVCC, it is used by modern DBs such as Postgres, Oracle, SQL Server. And as we discussed before, readers see a stable snapshot of data taken at the start of their query. Then writers create a new version of the row. What are the benefits? This is the important bit. The readers don't block the writers, and writers don't block the readers. So high concurrency. So just to quickly revisit, there were 2 versions of the data, 50-50 and 40-60. And when there are transactions coming, there is transaction 1, which is writing to the database, and it is not blocking transaction 2, which is just reading the database. So writers don't block the readers, and vice versa, because transaction 2 is simply looking at the value that has been committed by some previous transaction. Just to quickly recap, let's go through the use cases and summary for the read committed transaction. What are the pros? High concurrency and prevents dirty reads. What are the cons? Allows non-repeatable and phantom reads. This is a default isolation for PostgreSQL, Oracle, and SQL Server. And what is the use case? Unlike serializable transactions, this read committed isolation, it provides most high volume general purpose web applications and services. And in our modern world, where application load is a lot, then we can't always afford to make one transaction wait after the other. In that case, we can't block other transactions, and we come to this agreement that we have to implement read committed transaction. This is one option. So hopefully you like the video. It has been informative. If you like the video, please like it and share and subscribe to my channel. I'll see you in the next one. Thank you.